D1, Newton, and the scientific revolution of the 16th and 17th centuries. Here is Sir Isaac Newton, a mathematician, physicist. In fact, Wikipedia described Newton as a mathematician, an English mathematician, physicist, astronomer, alchemist, theologian, and author, described in his time as a natural philosopher. We're going to take a few moments here to talk about this scientific revolution of these 2 centuries and talk about what is science and the scientific method. It's good that we do that at some point in our course. Now, Newton, his work called the Principia or Principia, the mathematical principles of natural philosophy, this can be looked at, this masterpiece, as the culmination of the scientific revolution of the 2 centuries. So let's take a few moments to look at this. You have 5 European scientists that are going to make this possible, this big breakthrough. Now, these scientists are building on astronomical data and discoveries that took place over centuries and centuries and centuries. So they're building on other scientists like those in Egypt, the Egyptians, and China, the Chinese, Greeks, and the Arabs. And during the Dark Ages in the West, in Western part in Europe, you have the Arabs playing a major role in science for many, many centuries during this period from the fall of Rome to the Renaissance. And then the scientific revolution of the 16th and 17th centuries comes after the Renaissance. So here they are. The first is Copernicus. And Copernicus basically showed us something very important, that if the sun were considered the center, the planetary motion is easier to explain, because we're looking at a model that dates back to the Greeks that says the Earth is the center of the universe. And Copernicus, the Polish scientist, gives us the concept of the sun being at the center and things are easier to work out. That's called a heliocentric model instead of the geocentric, which the Earth is at the center. Tycho Brahe, next, the Danish astronomer, spent decades without a telescope, a naked eye with fancy instrumentation to measure positions of the planets. And this decades of information that he gathered was very powerful and important in getting accurate data that would then be used by other scientists to establish that the sun is at the center. And that's Kepler, next in line, the German mathematician astronomer who used Tycho Brahe's data to come up with 3 empirical laws of the heavens, and we're going to study those later. You know, where for example, one is where the planets go around the sun, where the sun is at a focal point of an ellipse. Now, we mentioned earlier that Newton dabbled in alchemy, or was an alchemist also. These two, Brahe and Kepler, their motivation is largely due to wanting to cast a good horoscope, to have this information. So here we have scientific discoveries, mixed in with horoscopes and alchemy at this time. Then comes Galileo, the Italian, and Galileo, among many things, invents the telescope, or one of the inventors of the telescope. When he heard that someone else had invented it, he basically promptly invented one of his own, as the story goes. And here he saw moons going around Jupiter. So he discovered the 4 Galilean moons named after him. And that's a big breakthrough because he showed that something was going around another object, not the Earth. Everything doesn't go around the Earth. And then we come to Isaac Newton, who gave us the laws of motion, which we'll be studying today, and the law of gravitation. And he then explained how the solar system works. Now we know it's the solar system inside of a very, very large universe. Now, the scientific method is interesting to talk about because there is a confusion over this. Over many years, I was asked from time to time to talk about the scientific method, with other faculty mainly. Like, what are you doing? Are you teaching the scientific method? And the scientific method as taught in grade schools basically emphasizes only one aspect of science, where you have a hypothesis and you have control variables and you work with that. Now, I've never did that because I'm a theoretical physicist, so I want to give you a definition of science that's better, that's broader than the narrow definition usually encountered in grade school books. And we use these 5 scientists to help us define science, the architects of the scientific revolution. So with Copernicus, the first is models. His model was simpler than the geocentric model when he put the sun at the center. And that's very important in science. We go for this most simple explanation. So the building of the model and simplicity in science. With Tycho Brahe, you have observation and data. Gathering data and making observations, very important in the scientific method. That's going to be a crucial component. Then mathematics. Kepler used mathematics with the data to show that the planets went around the sun in elliptical orbits. Mathematics is very important. Galileo, who actually gave us Newton's first law, which we call Newton's first law, and we'll talk about that. He did so many things, but I want to emphasize here his instrumentation, the discovery or invention of the telescope, which is instrumentation to extend the senses, our senses. That's very important in science. And then for Newton, unification, that he unified the laws of the heavens and the laws of, say, apples falling on earth. So he basically showed that the apple falling on the earth and the moon going around the earth, both due to the universal law of gravitation, as he called it. So that's the synthesis and unification, very, very important in science. So we're on safe grounds with this outline of the scientific method. Here I would like to point out here a little bit of philosophy. Back in the older days, it wasn't clear what science was going to be like, and Francis Bacon gave us some writings that were struggling to understand the new method that was evolving. So I'd like to read his aphorism 95 in the New Organon, which was published in 1620. Those who have worked in science have either been empirics or dogmatists. The former are like ants who only gather and use. The latter are like spiders who spin webs out of their own materials. The bee demonstrates a middle ground. The bee extracts substance from the flowers of the garden and field. It then transforms and digests it by a power of its own. Francis Bacon. In other words, the ant that gathers and moves around, and that's all they're going to do, that's getting too experimental. They're empirics. We refer to those as empirics. And then those that use theory to the excessive degree where they don't relate it to data are dogmatists. So some of the medieval scholastics would fall into that kind of a category, the so-called argument over how many angels dance on the head of a pin or something. So this is theory without the experiment. And when you have the empirics, you have like an observation without any analysis. So the B, which is the ideal for Francis Bacon, gathers data from the world and then uses theory, thinking about it, and analysis, and develops that way. That's what science is, the blend of data and analysis. Another good way to explain the scientific method, because there really is no one method. Is there one method to paint? Is there one method to do photography? Is there one method in journalism? Is there one method in playing football? No. So here I like to use a detective analogy. And here we have Sherlock Holmes, a creation by Sir Arthur Conan Doyle. Now, Arthur Conan Doyle and Newton, both British, and became knights. They were knighted. So Sir Isaac Newton and Sir Arthur Conan Doyle, both knights. Science is an art, much like a detective trying to solve a mystery. And here we're going to use everything at our disposal: observations, theoretical analysis, hunches, clues, measurements, testing samples, chance, luck, guessing, and control variables, everything. So you do whatever you can, but the bottom line is that your work is based on reason and logic, supported by observation and data. Science must be able to predict. In the case of physics, we predict with mathematical precision. That's our goal. Science is also reproducible. Other folks should be able to arrive at the same result. In the crime analogy, two detectives with different styles would come to the same conclusion. If not, we would say that the evidence is not enough, inconclusive, or maybe the methods of testing, we have to wait for better testing, like better DNA testing. So here it's important that it's reproducible. And when I watch on TV, there's some neat detective shows, and detectives have different personalities and they use different methods of approaching problem solving. However, they're going to reach the same conclusion, and that's important in science, that reproducibility. So also getting back to Isaac Newton and theories and science of great beauty with the universal law, he basically he was able to explain how the heavens work, celestial laws. He was able to derive, for example, the laws of Kepler, the empirical laws of Kepler. And this unification of the celestial and the terrestrial forces into one universal gravity, that inspired Einstein to try to unite gravity and his new theory of gravity called general relativity with electromagnetic ideas and electromagnetic theory. And that Einstein spent a generation on that. He didn't succeed, but that's what string theorists are trying to do now. And we have had success with unifying electromagnetic theory with the nuclear forces in 1960s, 1970s. And that is leading toward the study of unifying all the forces in nature. So a very important aspect of science. So I hope that gives you a good overview of what science is. And it is general, not restrictive in any sense.